Hi, my name is Dave Thibodeau. I'm a principal R&D engineer at Knowles Precision Devices in Casanova, New York. I've been with Knowles almost 4 years, and I have a career of over 42 years working in design and development of RF and microwave components and systems. Today, I'd like to discuss low-loss, high-Q S and C band filters. So what's out there? Our environment is full of RF and microwave signals caused by cell phones, radar systems, garage door openers and other remotes, microwave ovens, radio services, Wi-Fi, and other data and communication services. To the right, I've depicted a spectrum with a multitude of signals at different frequencies and amplitudes. So why a filter? Filter attenuates or removes unwanted signals from desired channel. To the right, you can see on the top that I've shown the desired channel in the middle of that spectrum. An ideal filter, as shown in the middle graph, is lossless, has a flat passband response, infinitely steep projection skirts, and infinite out-of-band attenuation. However, in the real world, real filters, as shown in the bottom plot, have loss, have passband slope and ripple. Rejection skirts have slope, and they have limited out-of-band rejection. So why put a filter in a receiver? Well, again, they attenuate or remove unwanted signals from a desired channel. Why are they unwanted? Because they can saturate receiver components, and they can combine with the desired signals to corrupt the information. To the right, I've shown our desired channel in the middle of that spectrum. I put a real filter over the top of that spectrum, and you can see the dashed lines represent the amount of attenuation as a result of the filter, and the solid lines at the underneath show the remaining signal after the filter application. The filter result is shown on the bottom. You see some of those signals have dropped out. They've gone below the noise floor. And other ones are reduced in amplitude for the attenuation from the filter. Hopefully what's left is a high signal in our desired channel and signals that are reduced enough in the remaining spectrum that they will not interfere with our desired channel. So a filter and a receiver defines the desired channel. It sets the channel bandwidth. It establishes the thermal noise floor. It has an equation of where the noise floor is equal to minus 174, which is the thermal noise floor, plus the noise figure of the channel, plus 10 times the log of the bandwidth of the channel. By setting the thermal noise floor as low as we can, it improves the system dynamic range. The filter is also part of the noise figure performance because it's not lossless. The filter also eliminates aliasing in the digital conversion by eliminated out-of-band signals so they don't corrupt the desired signals in our bandwidth. Why a filter and a transmitter? Again, filters attenuate or remove unwanted emissions from a broadcast signal. They can remove the LO, the IF signals, harmonics, second, third, etc. They can eliminate the third order spurious responses, which typically are the ones that are closest to the passband, just by the way signals add up, and also many N by M spurious responses that occur from the mixing of the LO and the IF or RF products. I've represented this again in the top graph on the right. They also aid in spec compliance to FCC and regulatory requirements by, again, knocking those signals down to a level where they meet the requirements and minimize cross-channel splatter, keeping the harmonics and other spurious products reduced to a level where they won't interfere with other channels in the vicinity. As you can see, the filter result of the real filter on the transmitted response shows that the signal levels are knocked down to a level hopefully below the regulatory requirements. So in digital conversion systems, we have higher sampling rates in newer ADC and DAC converters, changing our component chains. Data converters are moving closer to the antenna, shorter RF chains, fewer mixer and IF stages. This requires tighter filter performance with lower loss, sharper filter skirts, higher rejection levels, smaller size, and higher power handling. In the past, designers have used several methods to meet needs. More than one stage of gain and filtering requires higher loss, lower Q filters. Waveguide filters are large, heavy, expensive, but typically have very low loss. One-element filters are typically large, heavy, have SMA connectors, and limited to lower frequencies. Cavity filters are typically large, heavy, and use SMA connectors. Knowles has a new line of low-loss, high-Q S and C band filters, which offer many advantages. We have center frequencies from 2 to 6 gigahertz. We have them in surface mount wire-bound versions, have a small size, narrow bandwidths of 100 to 400 megahertz at the center frequencies, 2 to 6 gigahertz. You have low loss, 2 dB typical, in some cases is lower than 1 dB. Have high rejections of greater than 60 dB, close to the band edges. Return loss is better than 12 dB. They handle power greater than 50 watts CW. And the operating temperature is minus 55 to plus 125 degrees C. And they're lower cost compared to most other options. In summary, that new filters meet some of the new challenges in today's system design and meet the needs of older architectures. Thank you.